Okay. So I will talk about three things. I guess the first part will be about PCPs and constraint expanders. Trying to describe PCPs as a type of expander. Then I will talk about agreement expansion. Kind of the main thing I want to talk about. It's a kind of high-dimensional expansion that is an important component in PCP constructions. And there are certain questions regarding agreement that I think if we make progress in them, we would really be able to make progress on some important PCP questions. In particular, there is this specific question about agreement tests that will imply proof of the 2-to-1 conjecture. So this is what I will talk about at the last part. So kind of agreement on the Grassmannian over finite fields and kind of how it implies something called the 2-to-1 conjectures. Okay. So let me start. So since I don't know exactly, the audience seems a bit mixed with respect to what they know about these things. Let me tell you how I want to think about PCPs for this talk. So I have a system of, suppose I have n variables. Suppose they're Boolean. And I have a system of constraints. Maybe they are, it's like a 3-sat instance, so these are just 3 CNF clauses, or if you want, it's a system of equations over these variables. So the way I want to think about them is that I have n vertices, a vertex for every variable, so n vertices. And in assignment to the variables, it's like a labeling of the vertices. And they're Boolean, so it's just a 0-1 function on the vertices. And the constraints say, some assignments satisfy all of the constraints. So this will be, let's call this system of constraint phi. So sat, is this too low or is this still okay? So sat of phi is just all solutions. Okay, so this is like perfect solution. So this is a subset of 0, 1 to the n. And it's the set of all functions on the vertices that satisfy all the constraints. And then kind of pictorially, I will think of the constraints as, maybe triples if it's a 3 CNF. It can be pairs if it is some other problem.
The constraints are linear or not necessarily?
No, they're not linear. They can be anything. They can be linear, but they're arbitrary. So we have this set of solutions. And now, suppose I'm given some specific string A in 0, 1 to the n. And I want to know, is this a valid solution? So, is this a string? Does it belong to this set? Yes or no? And there's two things I can ask about it. One is, what is the distance of A to the set of satisfying assignments? Okay, I'm talking about Hamming distance. Okay, so if this set can be empty, by the way. If this system of constraints is not satisfiable, the set can just be empty. In this case, the distance will be 1. So I'm talking about relative distance. Okay? This is one kind of parameter I can measure. And another thing I can measure is just plug in the values of A into the constraints and see what fraction of the constraints are happy and being satisfied and what fraction reject. So let me denote it by reject phi of A. Okay? So these are two well-defined things. This parameter is a bit hard to calculate, right? I mean, just to understand what this set is, this is an NP-hard set. To know if it's empty or not is an NP-hard question. So definitely to calculate this distance, it's not so easy. On the other hand, to calculate this is very easy. You just plug in A to every one of the constraints and just see how many are unsatisfied. So it would be nice if this would have been kind of a good estimate for this, right? So this is something I want to entertain, right? So in fact, let's define this kind of Rayleigh quotient. Which is this fraction of unsatisfied constraints divided by the distance of A from sat phi. Of course, it only makes sense to do it for A's that are not in this set. But okay. And maybe I can even minimize over all A's not in this set. Let's ignore the case where this is the entire 0, 1 to the n. Suppose that's not the case. Okay, so define this, and actually, let me just say that I will call this the expansion of phi. Okay, I noted gamma of phi. Okay. So why am I calling it expansion? I will explain shortly, but just to explain what this is. You can think of the fraction of constraints, the constraints themselves that are unsatisfied as some kind of boundary, saying, you know, A wants to be inside this set, but there are these constraints that are not allowing it to be there. And if this thing is large, suppose it is, I don't know, bigger than some gamma 0, then it means that whenever this is small, meaning A is an assignment for which few constraints are unhappy, it must be that the distance of A from the set of satisfying assignment is also small, right? Because you move it here and you see that the distance is at most the fraction of unsatisfied constraints divided by some constant gamma 0. Okay? So when you have this lower bound, it means that whenever the boundary is small, you can be corrected. You can kind of change a few bits in your A to make it some other A that has 0 boundary. It's just perfect solution. This is kind of a very nice property to have for a system of equations. Why is it so nice? Because then I have this relationship between these two things. If I want to know, if someone tells me, look, here is a satisfying assignment for your system of constraints, I don't even need to check the entire thing. I select a random constraint, and I see if it's satisfied, and it gives me a good estimate to the fraction of unsatisfied constraints. Of course, not every constraint system has this nice ratio. You can imagine a system of constraints where almost all the constraints are satisfied by some solution, proposed solution. But if you try to fix this solution, you change one bit to fix this equation, then you ruin some other equation, then you change that bit to fix that equation, you ruin some other equation, and you will never kind of move to a satisfied solution. So
question here.
I hit it.
Yeah.
So just that you can justify your definition as a generalization of edge expansion, because if you define the constraint problem as the problem where you're trying to put all vertices on the same side of a cut, then the numerator becomes the number of edges that are cut, and the denominator becomes the maximum size of the set in the partition. So it's
you took my next slide.
Well made. Oh, okay.
Okay, perfect. So that's wonderful. Yeah, so what Russell is saying is that this is strictly a generalization of edge expansion. Okay, why? Because if you have a graph, you know, edge expansion of a graph is, how do we usually define it? We say it's the minimum over all subsets that are not, how do you say it? Not empty and not full of the number of edges between S and the complement, divided by the minimum between S and the complement, and the size of the complement. This is the standard definition for edge expansion. Now, if you think of the graph here, so I didn't write, but there is some underlying graph. You think of the graph as a system of constraints where every edge is an equality constraint. It just says, I want the value here to be equal to the value here. Then the function A that we're minimizing over is just like selecting a subset, right? And if the graph is connected, then the only functions that satisfy all the constraints are the constant functions, either the all zero or the all one function. And then the distance of some non-constant function to the set of constant functions just becomes this denominator, and the number of unsatisfied equality constraints are exactly the edges crossing from 0 to 1. It's exactly the numerator. I need to maybe divide by V over E. So it's a normalization. It's not important. You exactly recover this definition of edge expansion. So in other words, we have here some definition of constraint expansion, and there is a way to see that it's just a generalization of edge expansion, which is very nice. Now, what does this have to do with PCPs? Right? So it has everything to do with PCPs, because you can think of a PCP theorem as something like a transformation or an algorithm that expanderizes a system of constraints. So before I finish this thought, I want to go back here and say, as I started to say before, if I have a system of constraint that is already an expanding system of constraints in the sense that there is this lower bound, then I have a very good probabilistic way to check if an assignment is satisfying. I just select a random constraint, and I'm guaranteed that if the assignment was good, I will always accept. And if the assignment was far from a satisfying assignment, I will reject with probability proportional to the distance. So this is what you want in a PCP. And what I'm saying here is that the PCP theorem can be viewed as kind of an algorithm that takes a constraint system C1 over variables V1 and moves it to a constraint system C2 over variables V2, such that two things happen. First is that gamma of C2 is bigger than some gamma. So I should say here, there exists gamma bigger than 0, and an algorithm, this constant is universal, and then there's an algorithm that does this and creates a constraint system C2 that has this expansion. And also, there is a bijection between SAT C1 and SAT C2. Here's some questions. So I'm thinking of these as the constraints. And these are the variables. So you might need to introduce more variables here, not only the old variables. V2 is kind of a new set of variables and a new set of constraints over them. But the point is that there is a bijection between the set of satisfying assignments here and the set of satisfying assignments there. In particular, if this is empty, then this is empty. Okay? And so this is actually stronger than, strictly speaking, the PCP theorem, but certainly it's sufficient. Okay, so it's nice to think of the PCP theorem as some kind of expanderization algorithm.
So isn't in the PCP unique that you will have many non-satisfiable constraints even if you were very close to a solution?
No, actually what you say in the PCP theorem is that in the no case, this is empty. So this just needs to be empty, and then you're guaranteed, by definition, kind of the distance from the empty set is a constant, so it means that the reject is always going to be at least gamma 0 times 1. So, Okay, any more questions, actually?
This is true. It's true unlimited.
It's not quite known. So I'm trying to hide this under the rug. So I think this would be a very nice theorem, but I don't quite know how to prove it. But let's kind of ignore it. How do you say it? Like, it should be true, right? Or something like that. But,
So what's missing?
yeah, what's missing is actually in the yes case, this is a very strong guarantee. It says that for every A, the fraction of rejecting constraints is proportional to the distance from satisfying assignments. When you prove the PCP theorem, you say, if it is satisfiable, it remains satisfiable, and you ignore this fact that if it's satisfiable, you still want to get the right proportion. So this we don't have in the proof.
Is it not an important ingredient in the PCP that the constraints are bounded?
Yes. When I say constraint, that's correct. I'm implicitly thinking of constant.
You start with bounded and you are getting bounded.
You're getting, it's very important.
From the beginning.
Yeah, that's true.
So you're saying in the current proofs, the first bullet is known only when C1 is not satisfiable.
It's empty. When this is empty, yeah.
Yeah.
Okay. So let me say one open question that I think is important, and that is, get an algorithm that does this, but such that C2, the size of C2, is linear in the size of C1. Okay, this is it's a famous open question to construct a linear size PCP, and it has many applications. For example, if you believe that SAT only has exponential time algorithms, then does GAP-SAT also only have exponential time algorithm? And this would resolve that question. And in particular, this means also that I don't care that the algorithm will run in polynomial time. It can run in sub-exponential time. It's just that the output needs to be linear in the input. And I think it's a nice question. Okay.
In these new definitions, the distances, are they relative or absolute?
Relative. It's always between 0 and 1, yes.
And your distances also.
What do you mean? So this is a number between 0 and 1, and this is a number between 0 and 1, yes.
And it's defined to be 1 when it's
The
not
set is empty.
satisfiable?
Yes. Okay. So, how much time has passed? Let's see. I didn't start the timer. Okay. So this completes my first part of the introduction, and I hope now if you don't care so much about PCPs, at least I try to convince you that it has some kind of expander feeling inside of it. It has a natural kind of Rayleigh quotient in the definition, and this is something to keep in mind. Okay, this is some kind of expanderizing transformation. Okay. So now I want to talk about agreement. Agreement expansion. Which is really like the question that I care about, and I think it's really an important component in PCP constructions, as I said in the beginning, and it's also a type of high-dimensional expansion. So now I want to talk about these things. So first of all, I want to say how agreement expansion is a component in PCP construction. So I told you that the PCP is some kind of expanderization algorithm, but how would you do that? How do you prove such a thing? If you haven't seen these things, it looks very mysterious. How do you take a set of constraints and make a new one and so on? So let me tell you one thing. It's very easy, actually, to do this transformation if you don't insist on being efficient. If you allow me that C2 and V2 are, say, exponential or doubly exponential in the input size. Okay, essentially, the way we do it is we think of the new variables as encoding the old variables. We give a variable here for every possible function over the old variables. And then it's easy to generate constraints that check all the constraints. So I'm not going to show it. Just believe me that to generate kind of an expanderization when the output is very large, it's not so hard. It's like saying, the for edge expansion, if you allow me a dense graph, it's easy to construct an expander. Right? So maybe this is slightly less easy, but it's still not hard. So the main kind of point is, okay, what if we want this transformation to be efficient? Okay, so the way we do it is we look at the...
If you do the exponential or doubly exponential transformation, will you get the definition of expansion also for satisfiable?
Yes. Yes.
So that's lost in the composition.
The analysis gets lost. I don't know if the property gets lost. Yes. So, okay. So now let's look at this system of. So here is V1. I'm imagining V1 is just vertices, like I said before, and I'm not drawing them, but I also imagine the constraints as being, some triples over here or something like that. And now I want to construct this algorithm, this transformation. And the way we do it is we will break this V1 into small pieces like this. Okay? It's not exactly like this. The pieces will have to be overlapping. So the idea is to take pieces of these variables so that every constraint will occur at least in one of the pieces. And now, for each piece, we encode it using so let's say this is S1, S2, S3, S4. So each one of them we will now encode separately. E of S1, E of S2, like this. And this encoding is the inefficient, maybe doubly exponential or whatever encoding. But since S1 is maybe of constant size, we don't care. We allow ourselves to do this. So now, kind of a major part in proving this correctness is to say, okay, so we use some PCP transformation to encode each part. That's okay. So if we are given some proof here, we can check it probabilistically. But we need to also be able to make sure that when we are given a proof that is the concatenation of these proofs, these separate proofs can be glued back together into one global object. It's very.
An assignment.
The proof is an assignment to the variables. I mean, I guess here I have new variables that encode these variables, and here I have new variables that encode these variables. And if they intersect, I need to make sure that I can glue them back together again. Okay? Now let me stress that it is kind of unavoidable that these sets intersect. There's no way you can take a three-set formula and partition it into disjoint little formulas. Otherwise, it would be very easy to solve. Okay, so the overlap is inherent. And so this problem of stitching the things back together again is inherent. And this is the agreement question. So now we'll define it formally. So I have some universe. Okay, some finite set, okay, of vertices. It's this picture. And I have some collection of subsets. And how to think of this collection? So one possibility is to think of all possible subsets of n of size d. Another way to think of it is, say, the d-dimensional faces of a simplicial complex. But if you don't want to think of a simplicial complex, you can just think of all possible subsets of size d. Okay? And already at this point, let me already say that it is good if you have some group acting on this collection. It's good to think of this collection as being somewhat symmetrical. Okay? Because then you can expect that maybe you can use the representations of the group to do some harmonic analysis. So it's good to think of this as some kind of a symmetric thing. Okay, so we have a collection of subsets. These are these subsets. And now what is I'm going to define a local assignment. A local assignment is really a collection of local functions. One function for every subset. Okay, so it's something like this, f sub s, for all s in X, where f sub s is a function from s to 0, 1. 0, 1 is arbitrary. It could be some other alphabet. I don't care. So what is this thing? I guess some people think of this as something called a sheaf, where for every S, you have some space of functions that are allowed here. For this S, it's all the functions on these elements. For some other S, it's all the functions on that element. And there are some relationships between these functions, right? When you have a function here and a function here, the restriction to the intersection needs to be identical. Okay, so this is something that people define as a sheaf, and it's kind of, to me, it was a very nice discovery that this agreement question that I view as something very esoteric and specific to PCPs, later I discovered that actually, no, there is this terminology to discuss these things, and it's a very kind of a natural thing for some people. Okay, so another way to call it is cohomology with local coefficients. So we will hear later about coboundary expansion and other types of expansion where you take every set in, say, in a simplicial complex, and you label it with an element in a ring or in a field, say in F2. So for every S, you have an element in F2. Here, instead of having a field element for every set you have its own little vector space of allowed elements. And you label S1 by things from the vector space attached to S1. And you label S3 by something from the vector space attached to S3. This is exactly a sheaf. Okay. And the nice thing is that we can kind of study these kinds of definitions and maybe, get something out of it. So
just to make sure, what you didn't write is what we should be expecting, right? That Fs and Ft restricted to the intersection are the same, right?
Yeah, so let me write it now. So this is a local assignment. And an agreement test is that for every S1 and S2 that intersect, you want that Fs1 at any point x equals Fs2 at the same point x for every x in the intersection. Okay, so this is like, I'm thinking of this as one constraint. For the pair S1 and S2, I check that for all the elements in the intersection, these two local functions are they agree. This is an agreement test.
Just for terminology, something can be a local assignment even if it fails the assignment test.
Yes, so a local assignment is just a collection of local functions. It can be anything. And an agreement test looks at a local assignment and requires that these conditions hold. So now we can go back to the definition we had for constraint expanders and say, okay, who are the local assignments that satisfy all the agreement tests? Okay, so it depends on the collection of subsets. But when this collection is connected, these are only kind of global assignments. So a local assignment is global. There's some function g on the vertices, so these are all subsets of some, and vertices. So an assignment is global if there is some way to label the original vertices such that for every s, the local function f at s equals this global function restricted to s. This is kind of the desired object. This is what we want. We want to be able to stitch back these local functions to a global function. Okay, so these are kind of my good solutions, a global assignment. And now what is my question? The question is whether I have this notion of expansion. Let me first just define clearly. So let me say this: if x is connected, okay, whatever this means. So, I mean, there's a way to define it. If you think of X as a simplicial complex with different dimensions, it needs to be connected on all dimensions. But if this is true, then let me call F a local assignment is. Sorry, I need to define one more thing. So I defined what an agreement test is. And what I want to also define is this parameter. So let me say, is this pushing it? It's still okay. The agreement of F, so now for every F, it is a local function, a collection of these local functions, a local assignment. Agreement of F, what is this going to be? It's going to be the fraction of tests when I choose S1 and S2 at random that satisfy this agreement test. Okay, so the probability over choosing S1 and S2 such that this condition holds. Fs1 at x equals Fs2 at x for every x in S1, S2.
But you choose only pairs that intersect?
Yeah, okay, so that's I didn't say what is the distribution over these pairs, S1, S2. So this is important, actually, because if you just choose two subsets that intersect, you won't get a very good result. So let me leave right now the distribution kind of free, and we will discuss it a little bit later. Okay, so really, this parameter agreement, it should be parameterized by some distribution over how to choose the pairs. Okay? But, okay. For now, if you want, just think of what the way Noga said. Just choose two sets that intersect. That's fine. Okay, so now complete the sentence here. If X is connected, then a local assignment is global if and only if the agreement is 1. So, of course, if it is global, then all the agreement tests succeed. That's obvious. And if all the agreement tests succeed, you need some connectivity requirement to say that it means that it is global. So this is nice. And now there's a natural kind of approximation version of it. What if you tell me, here is some f, and I tell you that the agreement of f is 1 minus delta? Okay, so now the question is, suppose agreement of f is bigger than 1 minus delta. What does it mean about f? Does f have some structure? Okay, so is it true that f is close to f prime, which is global?
Close is how many distance?
Okay, and close is Hamming distance in the sense that it measures on how many subsets does f and f prime, do they agree? They have to agree exactly. Okay, so now this gives us this definition of the agreement expansion of this complex. It will be the minimum over all these functions f that are not global of the ratio between, so it's not going to be the agree, it's going to be the disagree. So let me write here disagree f divided by the distance of f from global. Exactly like we did before. Okay? So this is what we will call the agreement expansion. Now I see that I forgot to say, so this part is joined with Tali Kaufman.
It seems like you want to define alpha to be a function of x and d. In some sense, x are the vertices and d are the edges.
That's right. And this d is the distribution over pairs, S1 and S2. But
And then the distance of f from global would be measured under the marginal of D.
That's right. That's right. That's right. And but I will care about like the best distribution, the distribution that makes this as large as possible. I mean, kind of the name of the game is to find some x and some d, such that this thing is bounded below by a constant. Right? So if you give me x, I will look for the best d that I can to have this be large. Why do I want it to be large? Like before, it would mean that whenever I have f that has small disagreement, it means that it is of small distance to being global. We can correct it to make it a global function. Okay.
10 minutes.
Really, 10 minutes? Okay. So yeah, so what to do? I think it is a very interesting question just to study this in itself. Like, for what kinds of x's can you even get a constant agreement expansion? Now, what do we know? So these things have been studied kind of without calling them by this name in the PCP literature. And really, we studied kind of 2 or 3 different objects. One of which is the simplest, is the complete complex, just the collection of all k element subset or d element subsets. Right? And even for that, it is not trivial at all to prove that it has constant expansion. But it is a theorem. I mean, okay, there's a lot of works dealing with this, and we proved that this has agreement expansion with David Steuer maybe 3 years ago.
For what size of subsets?
Constant size subsets, yeah. I always think of kind of the size of the subset as being constant with respect to the universe, yeah. Okay, so now let me move to talk about, and let me say one more thing. So there's been a lot of interest in trying to find complexes that are sparser than the complete complex. The complete complex, if the subset has size k, it has n choose k elements, which is a lot.
The complete one, what would be the joint distribution?
Okay, that's a good question. It would be, say, 2 subsets that intersect on size k over 2, for example. Yeah, some linear intersection. So to understand whether you can get a sparse such complex seemed to be a very difficult question. And at some point, so there are de-randomizations. You can look at, instead of all subsets, there's a very beautiful paper of Russell and Pagliazzo and Avi Vigderson and Valentin Kabinets that suggest to use subspaces. So they suggest to think of this universe as a vector space. So it's some, instead of this, you look at some f to the n. And then the subset will be, it's the Grassmannian. It's just all, say, linear or affine subspaces of some dimension. And then they show that you can still prove some kind of expansion. It's not this kind exactly, but never mind. But it was not known at all how to do expansion, which is just to get expansion when the complex itself has size linear in n. So in all these complexes, the size is at least quadratic in n. Okay. And kind of right now with Tali, we're studying the agreement expansion for this Ramanujan complex defined by Alex Lubotsky and Samuel Zanvishny. And we believe that the expansion of this sparse complex should be really almost the same as the expansion of the complete complex. So we are able to prove some qualitative results, but not quantitative downs yet. So now,
so this is sparse as in having order of n sets.
Order of n sets, bounded degree. Every vertex participates in only a constant number of sets.
And the sets have constant size.
And the sets are constant size. It's quite an amazing object, because if you take a random such object, the sets will never intersect except on one vertex. So it's like an object that I would conjecture doesn't exist. And when I saw that it exists, very kind of
But don't the sets have to include the original constraints of the system? I mean,
no. So trying to abstract this question separately. Yeah, but it's true if, this question you can naturally define it as a sheaf, and then when you define the vector space you allow on every set, you can include different restrictions. For example, maybe you want that the values here, the function here is a linear function. In the example where each S is itself a linear subspace, it's very natural to require the function on this linear subspace to have some algebraic structure, maybe to be linear. Okay, and this is exactly what we look at in this work with Subash and Muli and Dor and Guy, where we look at the collection of subspace. So let me talk about it a few minutes, even though we won't have enough time to finish this. So I want to say a few things about a specific agreement question on the Grassmannian, which falls in this framework. And we have some hypothesis that if it's true, it would imply some conjectures that are very important for hardness of approximation, but let me skip that part because I won't have time to describe anything. Okay, so let me just give you some kind of concrete combinatorial question and we'll see. Okay, so here my universe will be just F2 to the n. Okay, and my collection of subsets will be just all L-dimensional linear subspaces. And my local functions, so now I'll call them L because they're subspaces instead of S's. Okay, so for every L in X, I have a local function which is required to be linear. So what we really think about is that there was a linear function over the entire vector space, but it got disintegrated and kind of broken into pieces. And for every linear subspace, there is a piece. And what we get is this local assignment. On every linear subspace, we get a linear function. Supposedly, all these linear functions come from one global linear function, but we need to check that this is true. Okay, so I have my collection of linear subspaces, and for each one I have a linear function. Now, what is the agreement test? We just choose two subspaces such that their intersection is maximal. Oops, dim is L minus 1. So, as I said before, it is important when you choose S1 and S2, not every distribution is the same as every other distribution. So kind of the key idea here, which it comes from an earlier work of Subash, Muli, and Dor. They have this kind of amazing idea to think that we will look at very, very large intersection, but still we will require a structure even when the agreement is very small. So I will say it in a minute, what I mean here. So the agreement test is choose two subspaces that have the largest possible intersection. I mean, if the dimension would have been more than L minus 1, they would just be the same subset. There's nothing to check. So they're just intersect slightly less than that. And you check agreement. Okay, so, and you look at the agreement. The agreement of F is really the probability of L1 and L2 from this distribution of that FL1 equals FL2 on every X in the intersection, for every X in the L1. Okay, so this is how we will define the agreement. Now we know we know how to prove this, that if the agreement is bigger than 1 minus delta for small enough delta, it means that F is close to global. And when I say here global, it is actually easy to prove that if you're close to global, it's not only that there will be some function on the vertices that you agree with, it will be linear. Second?
That's what.
Okay, so in this case, a global function will be a function on F2 to the n that is also linear on F2 to the n. Okay, but what we are interested in is what happens if we know that the agreement of F is just bigger than delta.
Just a second. If it's more than 1 minus delta, then it's close to global. This is a result, so this is a wishful thinking.
No, this is true. This is true.
That's what they call in the arithmetic complexity the 99%.
This is the 99%, and this is the 1%, right? So now in this question, actually in all these questions that have to do with large gaps in PCPs, so this is not new to this problem, you're interested not in the 99%, but rather in the 1%, where you only have some tiny non-negligible agreement. Before, I kept talking about this agreement being small implies you are close to some good function. That means that the agreement is 99%, and it means you can be corrected. This question is in a different regime where you know that the agreement is non-trivial. Why do I say non-trivial? I say non-trivial because you can think, for example, on a function, a collection of local functions that's random. For every subspace, you choose something at random. If you do that, when you look at two FL1 and FL2, you'd be very surprised if they agree on their intersection. The probability for that is 2 to the minus L minus 1. So very small. And here I'm thinking of delta as being some fixed, say 0.1. So independent of all the other parameters L and N. Okay, maybe I should have mentioned that L should be thought of here as very small compared to N. Although, I mean, I don't know how to solve it even if L is, say, N over 2. So anyway, the question is, what happens if the agreement is slightly non-trivial? Can you deduce any kind of global structure? Is F in some way close to being a global function? How many minutes do I?
-1.
Really? Okay. So, all right. So let me just use another minus half a minute to say. So there is something interesting here to try to understand what kind of structure you can expect. And this has to do with the structure of the links of this. So this is not a simplicial complex, this collection of subspaces. But still, it has the same kind of ranked, it's like a collection of subspaces of increasing dimensions. And they have relations with each other. And so there's this natural notion of a link, all subspaces that contain a given subspace, and also all subspaces that are contained in a given subspace. And these come into the picture when you try to understand what kind of structure is reasonable. So anyway, we don't know how to prove this, but we have a concrete hypothesis that, from which we know that the 2-to-1 conjecture will follow. But, okay, that will be enough.
Now you concentrate on this agreement type. I mean, is there some principle that every problem can be translated to agreement problem? This is like part of the discipline.
It's like empirically, agreement is important, but I don't have a theorem saying that.
Sometimes you test near again, sometimes you test the distances between these two, right in the PCP.
Yeah, there's various things you can do. For example, maybe you only want this not to happen for all, but for most.
So written this 99%, just like a very quick, is it actually possible that F is close to global, but not global? To me, my intuition says that if it's 99% on all this intersection, I mean, it kind of really has to be a satisfying assignment. But you're saying it doesn't have to be.
No, think of a local function that is perfectly global, and then you took some 1% of the subspaces and you just ruined them.
Well, I guess he says if it's linear and it's close, then maybe.
No, but you ruined them by changing them to another linear function, locally.
But suppose you want a global linear function. So all the global linear functions are far from each other. If you insist that you are close to something that is global and is linear,
You can still take something that's global and linear and take one subspace and change it to something else.
so I want to insist that it's linear.
To something else that's linear.
Only locally.
Yeah. Yeah. Okay. Okay.
If you want to use this machinery to reduce from maybe 3 link to 2-to-1 games. How big is L going to be? Is it like?
It's going to be a constant.
L is a constant.
It's a constant, yeah.
But then a random L-dimensional subspace will cover actual constraints of the drilling problem.
Yeah, so, yeah, I can show you offline, yeah.
Maybe we'll take the rest of the questions offline.